So we've been talking a lot about the force which acts on a current carrying conductor in a magnetic field. And now this next subject of our attention will be how do moving charges act in a magnetic field. So previously we've talked about this formula in this sense, that the force is BIL sine theta. So this is the angle between the current and the magnetic field lines. So really, if you think about charge, so charge is also, if you have current, so you know that's the rate of flow of charge. So we have this sort of an idea somehow that charges would also experience a force, right? Because current is nothing but the rate of flow of charge. But then if we talk about charge, then it really isn't flowing through any sort of a conductor, so the length is not really relevant here. So what should we do here to get an expression in terms of the charge? So it's a really easy derivation. And again, if we just follow what we just discussed, so B is the magnetic flux density, I, the current, can be written as the rate of flow of charge over time. So it's Q over some T, and this is some length. And this right here is not the length of the conductor. Instead, this is some length through which the charge moves. And then you have sine theta as it is. So if you think about this thing here, so all of L over T, so that's really just the length moved divided by the time in which that length is moved. So this is really just the linear velocity of the charge. So we can also write this equation like this. So it's BQV sine theta as the force which acts on a moving charge in a magnetic field. So this is also an important equation and will be used whenever we are dealing with charges in a magnetic field. So now let's go forward with this result in sight and in mind. So in light of this concept that we just discussed, you have another alternative definition for the magnetic field as well. So a magnetic field can also be defined like this. So the magnetic field is a region of space. Previously, if you remember, so we defined it as where a pole experiences a force. And then later when we studied F equals BIL sine theta. So we said it's the force experienced by a current carrying conductor. Now we can also say that this is the region where a moving charge experiences a force. So the only condition here is that the charge must not be stationary. It must be moving for it to experience a force. And you can also see that from the formula here. So if it's at rest, its velocity would be 0. So everything then here becomes 0. So about the sine theta, we already know that how similarly when the force on a conductor which was placed parallel to the field lines experienced no force. So similarly, the idea here is that if you have a charge which is moving parallel to the field lines, that would also not experience any force. So really there are two conditions here where no force can be experienced. So no force on a charge can be experienced in two ways. So no force on a charge in a magnetic field if either of the following happen. So if the charge is not moving, this is one way you can have no force, so V is 0. Or if it's moving parallel to the direction of the field. So if either of these conditions are true, so then in either of these cases you will not have any force which will be exerted on a charge in a magnetic field. So let's have a look at the sine theta reasoning, which we've previously looked at. That was in the case of a current carrying conductor. This is in terms of a moving charge. So exactly what we were talking about moments ago. If it's not moving either perpendicularly or parallel, we'll have to resolve the components. So this one, which is parallel to the magnetic field, will not experience any force, and this one which is perpendicular will experience the force. So as we were also doing in the other formula, F equals BIL sine theta, still the direction of the force will be found using Fleming's left hand rule. So again, thumb points in the direction of the force, first finger points in the direction of the current, first finger points in the direction of the field, and the second finger points in the direction of the current. Only thing you need to be careful about here is that when we use Fleming's left hand rule, what we call the current is basically the direction of the conventional current. So conventional current is taken to be the flow of positive charge. So here if we take something which is a negatively charged particle, so then for that the second finger must be pointing in the opposite direction to how the charge is moving. So for negative charges, the second finger must point opposite to however it's moving. So I can say opposite to direction of motion. Right? Now let's see this in action as well. So let's take two particles that we have here. So let's say this is some positively charged particle, and let's say this is a charge of positive Q, and it's moving in a direction like this. So it's moving with this direction, V, and you can see that this is perpendicular to the magnetic field like this. Again, let me mark here that here and in this case as well, B is the direction of the magnetic field. So how would the force act on this? So again, just a simple application of Fleming's left hand rule. So my first finger is field, that should be pointing upwards, and since this velocity is in a direction like this, so that's where my second finger should be pointing. So what I'll find is my force is in a third perpendicular direction like this. So this is how the force would be acting in this case. So that's the force. And here let's say that this particle which is here is some particle which has a charge of negative Q, and this particle is also moving in the exact same direction as the positively charged particle was. It's still perpendicular to the magnetic field like this. So if we want to find out the direction of the force on this particle, what we need to do is, since this is a negatively charged particle and if it's moving like this, then by Fleming's left hand rule the direction of current will be taken to be like this. So my first finger should point, my second finger should point in this direction. My first finger should point upwards. So what we'll find is that the direction of force on this particle is actually opposite. So that's something that you have to keep in mind when using Fleming's left hand rule for negative charges. So let's have a look at an example to see the application of this formula. So this question says an electron moving at 6.0 into 10 to the 5 meters per second passes perpendicularly through a magnetic field of this strength. The charge of this electron is 1.6 into 10 to the negative 19. What is the force? So F equals BQV sine theta. So since this passes perpendicularly, so this is basically sine 90, which is 1, and that just leaves us with BQV. So B is 2.0 into 10 to the negative 2. Q is 1.6 into 10 to the negative 19. And V is 6.0 into 10 to the 5. So that gives us the answer 1.9 into 10 to the negative 15 Newton, correct to 2SF. So in the next video, we'll be looking at more advanced applications of this very formula.